All right. Hopefully you survived the last video and you're ready for another one. Maybe you took a couple seconds to scream in an empty room or talk to your friends and your families about stats is weird, guys. We're talking about means of means. And they're going to say, what are you talking about? And you show them the video and then they start getting curious about stats. Maybe, all right, maybe this is a fantasy. Maybe this is not what happened. Let's talk some more. Let's talk about properties, right? Why, when I ask two professors, this is the students one. If I ask two students their favorite number and average them, there's a bigger variability, right? There's a bigger spread to the data than when I ask 25 students what their favorite number is and average the numbers, right? Because if I'm only asking two, then there's a bunch of different things that can happen. But the more people I ask before finding an average, right, the more like concentrated, right, the better the approximation is going to be. And if we asked everyone, then there would be no randomness at all. If our sample size was the whole population, however many students there are at SPSEC, there would be no randomness. There would be no distribution in this blue graph. If I asked everyone, if n were infinitely big, there'd be no variation at all. Because every time I took a sample, it'd be a census. I'd literally be asking everyone, and there'd be no randomness. So the more people I ask, the less randomness there is in the average response. Okay? So the average of the averages, the mean of these sample results is going to be random in general, but the more people I ask, the more consistent it's going to be. So what does that mean? I need a soundboard and like play groans. Like when I teach in person, I get to hear the groans, but I don't get to hear the groans. I just get to imagine you groaning at home or wherever. Let's do some properties. Let's get more concrete. Okay. So the sampling distribution model of means. So when I take a random sample from a population, population's everyone, random sample is just the people I'm asking. When I take a random sample from a population, and let's say this population has population mean mu and population standard deviation sigma. Again, for populations, we use mu and sigma. For samples, we use x bar and s. Okay. Well, when we do that, we have the following mean and standard deviation for the sampling distribution. Again, that sampling distribution is that blue graph from the web page. So this says the mean of the sampling distribution is the same thing as the mean from the population. Did we have that? The mean of the sampling distribution, the mean of each of these blue graphs, should be the same as the mean of the parent. Well, mean of the population was 16. Oh, great. The mean of the sampling distribution was also 16. And it also said that the standard deviation of the sampling distribution, the standard deviation of the blue graph, this, by the way, is also known as the standard error of the mean. So you hear standard error, that specifically means standard deviation of sampling distribution. That's a big word we're going to use a lot. So the standard error is the population standard deviation divided by the square root of the sample size. All right, remember n? Sample size. So here in our little example, here n was 2. Well, what is 5 divided by the square root of 2? Is it 3.54? I don't know, let's find out. 5 divided by the square root of 2. 3.54. Oh. Interesting. And that's why when n was 25, remember when n was 25, I said, look, 25 is this bottom one. The standard deviation is 1/5 the population standard deviation. Because if n is 25, what's the square root of 25? The square root of 25 is just 5. That's where that came from. It's all coming together, right? That's kind of cool. And remember that it doesn't matter, as long as the sample size is big enough, it doesn't matter what the shape of the parent population was. The shape of the sampling distribution will still be normal. And again, we can do super bizarre things, right? What if we have this distribution? This is a uniform distribution. Everything's the same. There's an equal probability. This is more accurate for favorite numbers. There's an equal probability that someone's favorite number is 0, as it is 5, as it is 32. Well, let's take a bunch. Again, if the sample size is big enough, it's still normal. Small sample size, this is not normal, right? It doesn't really quite fit with the normal curve, whereas this normal curve fits the bottom one really well, right? And you can see this with, you know, any we can make up our own thing right here, right? And do the same thing. As long as the sample size is big enough, it's normal, right? Look at this bottom one. N is 25. It looks normal. N equals 2? Yeah, no. Because we had a really wacky population distribution. Okay? So you need a big sample size if you have a wacky distribution. All right. So let's use some stuff. Let's connect the topics from Unit 5, normal distributions, with Unit 6, properties of a sampling distribution. Okay? So, example 1. Let's say that a person's measured glucose level 1 hour after ingesting a sugary drink, soda, juice. I'm sure there are more sugary drinks. And so their glucose level an hour after ingesting a sugary drink varies like with a normal distribution. So the average glucose level is going to be about 125 milligrams per deciliter. And the standard deviation is going to be 10 milligrams per deciliter. Remember that the units of the mean, the units of the standard deviation, oh, there's no space there, and the units of the data are all going to be the same. So part A, if we're looking at a single glucose measurement, what kind of distribution do we have? Well, it told us, right? Let X, right, be the random variable. So let X be the random variable. Let's see, of random variable of a random person's glucose level. An hour after ingesting a sugary drink. ... Well, then it literally told us X is normally distributed with a mean of 125 milligrams per deciliter and a standard deviation of 10 milligrams per deciliter. So when it says define the distribution, that's what that means. What's our random variable? And what rule does probability follow for that random variable? Well, it's like a bell curve. It's normally distributed. That's where the average is, and that's the standard deviation. And it also wants us to draw it. Okay? So every drawing of a normal distribution looks basically the same. Right? We have a bell curve. Ooh, that's actually not a bad bell curve. Usually my drawings are really bad. The average in the bell curve, that's that hump, going to be 125. And then one standard deviation is around the inflection point. That's going to be 135. All right, we're adding a standard deviation. We're adding 10 to our mean. That's about where that is. And then again, one more is going to be at 145. One more is 155. And you can do the same thing in the opposite direction. All right, 115, 105, and 95. And remember the empirical rule. Empirical rule says that about 68% of the data is within one standard deviation of the mean. About 95% of the data is within 2 standard deviations of the mean. Okay? 95% of the area is this red area. All right, so when it said draw the distribution, that's what it meant. Finally, what's the probability that a single measurement is greater than 140? That's asking what's the probability that a single value of x is at least 140. The probability that we're at least 140 is this area to the right of 140. And how do we calculate that? Well, there's a lot of different ways, but in this class, we used GeoGebra. Said, oh, GeoGebra, we need a normal distribution. So we went over to GeoGebra's probability function. And again, there are other ways of doing this. We type in the mean, it's 125. And the standard deviation of 10. What's the probability that we are at least, so at least means this button right here, 140. It's that area, which is about 6.68%. Okay? About 6.68%. So we defined the distribution, we drew the distribution, and we answered the question. And you might say, Jason, example 1A, that doesn't use this new stuff at all. You're right. This is old stuff. Stuff about normal distributions. Part B, that's where we're showing the distinction between what we used to be talking about and what we're talking about now. A single value for this random variable. A single person. Sample size of 1 follows the old rules. But if we're looking at the average value of multiple people, that has to do with a sampling distribution. So in part B, if measurements are made on 3 different occasions, if we're looking at 3 people, and we're looking at the average of their results, sampling Joe, Jerry, and Jameson, I don't know why they all have J's. I guess I'm only thinking about people like me, which is, I guess, very human, although not good. Anyway, let's say we sample 3 people and find their average glucose levels. That's going to behave a little differently. It's going to be random, depending on who we ask. Which 3 people we ask. Maybe we'll do a simple random sample. Maybe we'll do a stratified sample. Maybe we'll do systematic sampling. But no matter, even if we use the same method, it's going to be different every time. This is a random variable. The average of these 3 people's glucose level is a random variable. Discuss the conditions required to use a sampling distribution for this average. So these conditions that we need are these conditions up here. Independence, randomization, and sample size. Okay. Independence, randomization, and sample size. So initially you might say, Jason, you just said the sample size was 3. Are we going to have that? Well, remember, if you look, if the population is normal, there's no sample size condition. If it's not normal, we're going to need something bigger. 30 is a good rule of thumb. Like, right, 30 is rule of thumb. It's not always accurate, but it's a good ballpark number to have in your head. I can't spell thumb, so I'm just squiggling in the middle, apparently. All right, but either way, right, parent population is normal. So because the parent population is normal, we don't have to worry about the sample size requirement. Check. All right, so as long as each of these samples are independent and random, we'll be good to go. And there's some more we could say about that that gets into like heavier theory than we're going to cover in this class. But we're just going to say, yeah, we have these. But we do need each one of these. So these people have to be independent, right? Like we can't just be asking, oh yeah, let's pick a family of 3. That's not going to be independent. All right, so we have to pick 3 independent people. Right, like no necessary relationship. And it has to be perfectly random. Okay, so we can't just choose a name that we like on the list. Maybe we'll do a simple random sample. Okay. So some way to make sure it's random. As long as we have all these, then the central limit theorem tells us if we have all these 3, then we can model the average as a normal distribution. Right? If we have all of these ones, then we can model the average with a normal distribution. Okay. Define the sampling distribution model and its parameters. So let X bar, let's use capital X bar to show the distribution of the sample means little x bar, right? Little x bar is the sample means. The distribution of that can be shown with a random variable, capital X bar. Let capital X bar be a random variable, and specifically the random variable of the mean of 3 random respondents' glucose levels. So X bar, how is that distributed? The central limit theorem says that as long as we have all 3 of these, X bar is a normal random variable. And specifically, it's a normal random variable with mean of mu and standard error, or standard deviation, sigma divided by the square root of n. So the mean is going to be exactly the same as the population. But the standard deviation, that's going to be the population standard deviation divided by the square root of n. And n here is 3. Okay, so what's 10 divided by the square root of 3? I have no idea. 10 divided by the square root of 3 is going to be about 5.7735. Let's use more decimals. 5.7735. So define the sampling distribution model and its parameters. Check. Draw and label. Specifically, draw and label relative to the model in part A. And we're running out of space here a little bit for this. Here's what we're going to do. Let's let's go to a blank piece of paper. I think. Let's just do it down here, actually. Okay, so our original, right, had a mean of 125 and then a standard deviation of 10, right? So 125, 135, 145, 155, like so, right? This was our original. Oops. I'm just copying our original down. Well, then let's also do this one right next to it. So let's do the sampling distribution in red or some other color. Well, it's going to have the same mean, still going to be centered at 125, but now the standard deviation is much smaller, right? Standard deviation is a little bit more than half the size. All right, that's one standard deviation. Another standard deviation, another standard deviation. Okay. The first standard deviation is going to be about a little over 130, which is like right here. Do that in both directions. All right, it's going to be about 130.8. This is going to be 119.2. And then you can keep on counting those standard deviations, but they should be the same distance apart. And you should get something that looks a little like this for the 3 standard deviations. So the top is still the same, but now the inflection point kind of goes right here, and it gets smaller much faster. Has the same mean. The distribution of x bar has the same mean as the distribution of x, but a much smaller standard deviation, much less spread. Okay. So we did that over here. Part D. What's the probability that the mean of 3 measurements is at least 140? So it seems similar. In A, we said, what's the probability that a single measurement is at least 140? And we said, okay, the probability of a single measurement being at least 140 is this red area. Well, the probability that the average, right, that the 3 is at least 140 is going to be different. That's what's the probability that x bar is at least 140. That's going to have to do with our red distribution. Well, this is about 130 right here. This is about 135. This is about 140. So notice this blue area. Compare this blue area with this blue area, right? The probability of the average being 140 is going to be way smaller. Oh no, I erased the wrong thing. I knew that was going to happen. All right. Disaster. So how do we find this probability out? Again, x bar is also a normal random variable. So let's just type in these new parameters into GeoGebra. Okay. Same mean, but now the standard deviation is 5.7 something. 7735. 7735. What's the chance that we're over 140? Now it's only 0.47%. So if we're only asking one person, if we're only checking one person's glucose level, it's about 7%. But if we're asking 3 people their glucose level, measuring 3 glucose levels and finding the average, well, the chance the average is at least 140 is way smaller. This should make sense, right? This is an unusual event. So getting one unusual event, that's unusual. That's the definition, right? But doing it 3 times and having the average still be unusual, that should be much more rare. If we look at n equals 10, that'd be even more rare that the average would be so bizarre. That's what we're talking about here. And this is interesting because when we take samples, a lot of times we don't know the parent population, right? The whole point of sampling is to approximate the population. So by investigating the relationship between the population and these sample means, we're doing it right now when we know both, but it's useful if we don't know both. How can we compare these? What things does this X bar tell us about the actual population? There's very, very interesting things that we can do with this. Finally, what's the 95th percentile for this average? So that's the 95th percentile with a sampling distribution. Remember 95th, so sampling distribution means we're still going to use this mu and sigma. Percentile is the number that's above that much of the data. So 95th percentile is just when are we above 95% of the data. Type in 95% down here. Above 95% of the data at about 130.5. $130.5. What are, 134.5. And what are our units here? Milligrams per deciliter. I like drawing my L's like this. Okay, so the average of 3 results is 134.5 for the 95th percentile. You're very rarely going to get an average above this. All right, so let me know if you have any questions. The next video is some more practice problems using these sampling distributions. And then in the second half of this unit, we'll talk about sampling distributions, not of means, but of proportions. Remember, a lot of times we use means for quantitative or numerical data. And a lot of times we talk about proportions for categorical data. So right now we're focusing on numerical data, means, favorite numbers. Later we'll talk about categorical data, proportions, what percentage of people approved of this measure. What percentage of the coins came out heads, categorical data. Okay, good luck, enjoy.